This video displays the performance of our most successful controller, Controller 3, both for a zero steady state and a sinusoidal reference. As shown, the controller demonstrates disturbance rejection. However, it appears to have a lightly damped response. Classical control theory typically assumes a single input, single output system, which was the assumption held in this project. In this case, control is applied only to the pendulum arm angle, not the rotor arm speed. As a result, it is occasionally necessary to introduce a disturbance in the opposite direction of the rotor arm's motion to prevent its velocity from becoming unbounded, as seen in this instance. Controller 3's positive overshoot was positive 5.22 degrees, and its negative overshoot was negative 4.72 degrees. Controller 3 seems to oscillate around the zero steady state instead of converging, likely because the complex zeros in the controller dominate over the real poles of the plant. Although the integrator should ideally drive the air to zero over time, the rotor arm's current output suggests that the system's gain was too high, causing the controller's proportional control effort to become oversaturated and causing it to behave more like bang-bang control. The naturally oscillatory and shaky response of this controller configuration proved well suited to the sinusoidal reference and required notably fewer disturbances to correct the rotor arm speed. In the sinusoidal tracking case, positive and negative overshoots, after accounting for the desired pendulum set point, were positive 4.24 degrees and negative 4.36 degrees respectively. This performance was better than expected, though the system still exhibited a bang-bang style output in the rotor arm current. Following consultation with Dr. Buckner, an additional test was conducted incorporating a counterweight. Prior to viewing the inverted pendulum demonstrations under this configuration, it should be noted that the counterweight is not clearly visible in the video footage due to limited resolution. To confirm its inclusion, the following video features verification from the teaching assistant affirming that all subsequent test runs were performed with the counterweight attached.
All right, you're on air.
The counterweight was indeed on. I dropped it on there. We weighed it, 98.15 grams. Yep.
For which group?
For Trevor and Kai Green.
Yes.
Thank you.
Controller 3 tracking a zero reference exhibited positive and negative overshoots of positive 3.94 degrees and negative 3.4 degrees, respectively, with the counterweight attached. Controller 3's sinusoidal tracking exhibited positive and negative overshoots of positive 8.88 degrees and negative 3.94 degrees, respectively, with the counterweight attached. We were initially concerned that the 9.15 gram counterweight would significantly impact system dynamics, particularly given the rotor arm's 24.1% sensitivity in the phi double dot equation of motion. However, the total moment of inertia increased only by 2.67%. Experimentally, this corresponded in a 21% reduction in pendulum standard deviation during the zero reference tracking, though it also resulted in a 250% increase in required disturbance interventions. For sinusoidal tracking, standard deviation improved by 15%, while disturbance interventions rose by 150%. Although these trends are consistent with the rotor arm's sensitivity, these results remain inconclusive.